Welcome everybody. We are this afternoon in the session, the series of meeting the experts. This afternoon we are joined by Almudena, Majano and Antonio Lara. They have been in the framework of Studio 2. We have had a really nice Studio 2 projects jury with a very good insight. And we are very happy to have them lecturing. It has been for many years we wanted to invite them, but circumstances were not possible. But we have had their feedback many years, so we have been collaborating, and we really like their academic work. They are international timber experts in the design of structural works and also in the engineering. And I think for us it has been really helpful, their insight. And we do believe the computational design, it is very well used when it comes to solve problems and make rational use of the geometry. And the feedback, what we're commenting about, it's about first designing the system, the joints, and then adapting these systems to whatever purpose. So we are very happy that they are here today. Okay, and without further ado, I leave you with Dr. Majano.
Thank you, Enrique, for your presentation. The pleasure is for me. I'm really happy to have this opportunity of sharing with you the work that we have developed in the last years in the field of elastic timber GridShells that, kind of make us rethinking some of the main important parameters in the design of this kind of structure, like, for example, the material of the numerical model, of the construction that we will talk about later. So yes, I hope you find it interesting, and I will start first with an introduction. Okay, when we think of a shell, maybe probably come to our mind is this kind of concrete shell designed by Candela or Isler or Torroja. This shell, all of you know, is a three-dimensional curved structure that one dimension is much smaller than the other two. And they should be or can be built with simple curvature, like, for example, a cylindrical shape, or it can have double curvature, like, for example, I don't know, a dome, or this kind of shell, hyperbolic paraboloid shape. But the most important thing is that it must have curvature, because curvature make possible to balance out-of-plane loads just within plane stresses, okay? Reducing moment very much and making it a highly efficient structure. As you know, for example, concrete can be a very good material for these double shape shells, but how could we build it in timber? How could be a shell in timber? This picture I like really much. This is I'm always fascinated with these timber frameworks for building this kind of concrete shells. In this case, this Cuernavaca chapel designed by Candela is a parabolic paraboloid, so you know that this is a rule shape, so it can be built with straight planks, okay? What is missing in this timber framework to become a true self-supported shell? Imagine that this is the longitudinal direction of the planks, okay? So we know that in this direction, in this longitudinal direction, the planks can resist axial loads very well. But what's happening in the perpendicular direction to the planks? The situation changed very much, as we were talking before in the corrections. And the answer is here in the internal structure of the material, because we know that wood is a very clearly directional material. It is formed by fibers. The fibers grow in the longitudinal direction of the trunk. So it is clearly, the longitudinal is clearly the main orthotropic direction. And you have to imagine the internal structure like a bundle of hollow tubes that is represented here. Here we have the representation of the behavior in compression, here in tension, And this is the relation of the strength with the angle of the load with respect the grain of the material, okay? So it is quite obvious that in the longitudinal direction, the wood resists quite much, you see here, even if we are in compression or we are in tension in 0 degrees, no problem, it resists a lot. But what happens in the perpendicular direction? When the action is of compression, you see here, the strength goes down to 20% of the longitudinal strength. Okay, so it reduces very much, really. The tubes are crushed to each other. Remember that they are hollow, leading in a failure with some kind of ductility. Okay, but when we are in tension perpendicular to the grain, the situation is even more critical, because here we have no strength. That is what we talked about before, you see? So the fibers separate from each other, leading to a brittle failure, and we should always avoid this in our design. So it is this is the most critical situation, tensile parallel to the perpendicular to the grain, and we have to design understanding this behavior of timber. So now, if we come back to this Cuernavaca chapel, now we understand well then that here these planks cannot resist at all these yellow loads, because they are axial loads perpendicular to the grain of the planks, even if they are glued together at the side. The wood will failure. Okay? How can we solve this problem? Well, the solution is conceptually very, very easy. We can overlap by overlapping of cross layers. So in this way, our element can resist normal stresses in any direction. Okay? But we have to resist always also shear stresses. So what can we do for resist normal and shear stresses? We have, of course, we have to add a system that provides diagonal resistance. Okay? We can do it in two ways. Gluing at least two cross layers, one at the top of each other, with glue in between. Or if we want to use nails, for example, we have to nail at least 3 cross layers with different directions. So in this way, we could resist normal and stresses. So, and if we add to these two solutions also curvature, like here, we not only resist in-plane loads, but also out-of-plane loads. Good? So curvature is always good. So now we have the answer to what was missing in this timber formwork of the Cuernavaca chapel before. And now I show here another example of a shell with the same paraboloid shape, like the Cuernavaca chapel. And this they solve with 2 diagonal layers of wood glued together, making the pressure with nails. Good? The problem is that always gluing on site is quite a delicate process. It's a challenging process because glue always required control environmental conditions of temperature and humidity. So when we make it outside, it's really quite tricky. Okay? An alternative could be use glue products with cross-laminated layers, like, for example, plywood, CLT, LVL in the Q version, because all of these products come glue already from the factory. Okay? And I think this is the trend of using this kind of glue cross products. What is the trend in the current continuous cells nowadays? So depending how these surface elements are used, I think we could divide it in 3 groups or major groups of continuous cells. We could have continuous cells using flat elements or box-type elements. This you know already, and they are called plate cells. I think it's the most widespread solution of continuous cells, but the problem is here that they usually need this kind of sophisticated machines to make the mechanization of the contact planes, this kind of six-axis robotic arms. Okay. We have another option, we have, or another group, the continuous cell using carved glue laminated element, that is pre-curved element that are glued at the factory. These laminations of double curve elements are quite complex and costly because they usually need special molds, like you see here. They also need this kind of machines for the mechanization. So they are again costly processes and difficult processes. This is because there are not so many experiences of this group until now. And we have a third group that is continuous cell using elastically carved elements, that is post-curved element. This is a surface initially flat members that are carved on site to get the final shape, like you see here in this elephant park work. Really nice. But we could also build cells using linear members instead of surface elements. And we similarly could divide it in three groups. Grid cell, you know, all of you know that they are called grid cells, so we should have grid cells using these continuous straight members, where all the complexity is in the node. They used to be still nodes, like here. We have also grid cell of continuous curved glue laminated members, pre-curved member, that we have the same problem as before, this kind of members with double curvature. They have bending in both axes of inertia and also torsion, so quite costly, again, quite difficult to manufacture, and also difficult transportation to the work. In fact, in Spain, there are no companies at all that can fabricate this kind of elements. There are few companies in Germany and Switzerland, but the cost of these elements is between 5 and 10 times higher than if the element is straight or with a simple curve. So, quite difficult. And the third group is grid cells made of continuous elastically carved members. That is, members of very small cross-section and grid length that again can carve outside to get the final shape, like they are doing here. With this solution, we avoid to have these complexities, and also the nodes used to be very simple and very standardized, so we don't have this kind of complexity nodes that we show in this first group. So it is, and in this, they are usually known as elastic timber grid cell or strain timber grid cells, and this is the kind that we have worked in the last years, and will be the group or the kind of grid cell that I will focus the rest of my presentation. Okay, so now I would like to show you some of our works. One that we did some years ago, an elastic timber grid cell, and another works in progress that are not finished yet. But before, I would like to talk about some of the, let's say, key points, or key aspects in the design of this kind of structures. I will start with the structural and construction concept. It is based in two ideas. The elastic deformation of lattice, of course, they provide a lot of stresses, but the most important one are the bending stresses. So we know how to calculate them, or I think you know how to calculate it. It's very easy with the formulation of the strength of materials, and they are directly proportional, the initial bending stresses, They are directly proportional to the modulus of elasticity of the material, to the lath thickness, and inversely proportional to the radius of curvature. Okay? And these initial bending stresses due to the carving process must be less than the strength of the material. So we have to control really good this kind of ratio that is depend of the geometry that we are designing. When the out-of-plate bending stiffness is not enough, you can guess that going to higher lath thicknesses is not an option, because we will increase this initial bending stress. So the solution is to go to multi-layer systems. That is how they are being solved most of the elastic timber GridShells built to date. So in this way, going to multi-layer system, we can bend each layer independently, connect it afterwards. So we keep the stress in each lath, and we have a composite section with high strength and high stiffness. Here you can see some of the solutions of joints for these multi-layer systems. It can be made at the node, or it can be made at the lath, you see, with these CR blocks. That is a piece of timber here in between, or at both sides. We can join here at the node and also at the lath. There are different solutions that depend on the construction process that we will want to follow. And then, this is what we talked before. When we want to resist not only normal but shear stresses also, we need a diagonal resistance. And we could get it, of course, this is a bracing, we need a bracing system. And we could get it, for example, I don't know, with a diagonal cable, or we can get it with a diagonal lath of timber, or we could use also a panel or a board to give this diaphragm behavior. Okay? We could also do these rigid joints as we talked before, but they are more difficult to get. Okay, so this is the three main ideas of the structural concept. And I will talk now about the construction concept. Maybe there are two main construction concepts developed in the second half of the 20th century, let's say. One is the Frey-Otto's concept, Professor Frey-Otto of the IL in Stuttgart. I'm sure you know it. And it is based of the idea that initially flat quadrangular grid of constant spaced node, pin node, are transformed into double curved shape. So the erection process is a complete grid. The lath has bending in the two axes of inertia, and this is because the cross-section used to be a square. They are really small. The thickness used to be 35 millimeters to 50, and the wide under 80 millimeters. And the second construction concept is the concept developed by engineer Julius Natterer from Switzerland. And this is based on the mechanical lamination by nailing of different layers of geodesic lath. So we have a geodesic machine. The erection process in this case is lath by lath. That is, we bend one lath, we put nails, we bend another lath, we put nails. Realize that the nails are not drawn in this picture, but all the laths are nailing together. So they are, I said, geodesic lines, so the lath has bending on just a single axis of inertia, and this is why they used to have higher widths than the other previous concept, okay? It used to be 160 or even more. This is typical numbers for the wide. Here we see some examples. Maybe you know them, I'm sure. This is samples following the Frey-Otto concept. We have here the multi-hall in Mannheim of 1975. It is a really, really impressive structure. Antonio and me visited it, I think, 4 years ago, something like that. And impressive to be down this structure when you look up. It's really, yeah, admirable. The span is 60 meters, solved with cross-section of 50 times 50 square millimeters. So really small. And the slenderness, you know, there is the ratio between the span and the bending depth. Our bending depth here is 50 plus 50 plus 50. We have 150. Is 400, really, really high. It's even higher than Excel, that is used to be 300. Yeah? 400. And these other two are the Well-Endowed Living Museum GridShells and the Savile Garden GridShells. Both of them are built in UK. They're a little bit more actual, 2002 and 2006. They solve a span of 50 meters and 25 meters respectively, and the cross-section 50 times 35, 80 times 50 square millimeters, with also high slenderness, higher than 100. So quite nice, all of them. And this one that appears here, the Polydome in Switzerland, it's one spheric cap. This is one work, or one GridShells, following the Natterer concept, the second one that I explained before. You see here the cross-section of the lath. It's solved in a span of 25 meters, and the cross-section this time you see is a little bit wider, 120 times 27 square millimeters, and also high slenderness. And we see that in all the cases, we have solving largest span structures with maximum 50 millimeters thickness. So they are all of them very, very highly efficient, and yeah, with very small or small quantity of timber. No? So after seeing this concept of elastic timber GridShells, I will now present the GridShells that we built some years ago, all the works that we've done. We call PEMADE GridShells. It is built in Lugo. Lugo is in the northern part of Spain, in Galicia. And it was developed in the framework of a research project funded by the European Union. It was called Lugo Plus Biodynamic. And our work in this research project was to develop architectural and structural solutions using local timber, Galician timber. Maybe one of the, or couple of singular features of this elastic timber GridShells, one is the species that we use. We use Eucalyptus globulus. And the second feature is the structural scheme. It's a long cell supported only on the short side. But I will talk more about this later. I would like first to start with the design. This is, it was designed to cover a good store facility at the Timber Engineering Laboratory of the University of Santiago de Compostela at Lugo. And it is 24 meters long, 15 meters span, to allow the storage of long timber elements before and after testing them at the laboratory. And it has 7.5 meters of highest elevation and 4.5 meters free from, considering big lorries. And it is the first elastic timber GridShells built in Spain, and permanent, with permanent charreted, and the first worldwide made with Eucalyptus globulus wood. Here you can see explode view of the structure, and as I mentioned, part of the species, maybe the major interest, is the structural concept. It's a long shape supported on the short side, as I mentioned, on two glulam arches of 3 meters radius. This was quite a novelty and a challenge, because all the previous elastic timber GridShells that were built until now were supported around the whole perimeter. So this new concept offers other interesting architectural applications. It works longitudinally, like a big beam, So it makes cantilevers very interesting for reducing moment at mid-span, and also rotation at the support, and also protecting the storage wood from the rain. This, the grid layout, as you can see, is formed by two families of lats in the longitudinal direction, creating kind of a diamond pattern, and another family of lat in the transversal direction that are triangulates the surface, and also acting as a bracing system that we talked that is what we need. It is a double layer cell, so it has a double layer of longitudinal lats and also double layer of these transversal direction lats. The glulam arches rest on steel cylindrical support embedded at the foundation, and the grid shell is covered by a translucent white textile. Good, so we will see now the design process that we follow. It was an iterative process between the design and the structural analysis stages to get the final shape and meshing, and we created, developed an integrated design tool that was composed by 5 tools: grid build tool to mesh the surface, bending evaluation tool to provide the initial bending stresses due to the carving process, an optimization tool to provide or gives the minimal initial bending stresses, graphic output that gives the 3D model, and the data output to provide the list of data needed for the numerical model. So I will see very, very quick these 3 first grid tools. Starting with the grid build tool, it performs the surface meshing following a geometrical approach, applying the compass method, so we get a Chebyshev net. I am sure you know how it functions. Here we have the concept. We have a surface. We first draw 2 lines on the surface. Then these 2 lines are divided in equal segments by spheres with equal radius. And then using the intersection of the spheres with the surface, we get the centers of the new spheres, so the complete surface can be meshed. And we have this concept applied here on the right to the PEMADE grid cell. The 2 master curves were geodesics. Here we have the extended surface, the trim surface, and here the family of lats. Here we see, of course, also the grid build tool also drawn a part of the main grid, the bracing system, and the multi-layer grid by introducing the lag thickness. How does bending evaluation tool works? It first calculates the normal and geodesic curvatures with trigonometric relationship between the vectors of Frenet and Darboux 3 hydrals. Here we have them. And this is quite easy because first the tool can, or we can calculate the curvature with Grasshopper, very easy. I know you know how to do it. And then we can get the normal curvature by projecting the vector curvature onto the vector n, this blue here. This vector n is perpendicular to the surface at the same point of the curve where we calculate the curvature, you see? And then we can get the geodesic curvature by projecting this curvature vector again, but this time onto the vector g. Where is the vector g here? The vector g is here, and is perpendicular at the same time to vector g, is the tangent vector to the curve, and is perpendicular at the same time to vector n, that is the vector I mentioned, perpendicular to the surface. So we could do the cross product of these 2 vectors to get the g, so now we could project easily. So conceptually it's simple. Once we have this normal and geodesic curvature, the bending evaluation tool calculates the moments and calculate the initial stresses, the initial bending stresses. So we have both. We could have the total. And here is a representation, an example of representation of the initial bending stresses due, in this case, to the normal curvature. Well, so afterward we did an optimization to get the minimum initial bending stresses at these areas in blue, at the area of the support, because in this area are the highest moments. And using 4 genes, using as genes the origin position of the two master curves, of the starting point, sorry, the grid, the angle of the between the two master curves, and the cross section of the lath. So, of course, fitting or some architectural requirements, like, for example, the intersection distance to the boundaries, like we see here, in order to get a good design then for the anchorage of the textile at the borders, for example. Good, so this is very quick, the design process. So now I would like to show you some engineering details and construction, and how was the construction. The first step, of course, was to get the material for building the grid. This is a picture of manufacturing the lath of the grid cell. We use a product called finger-jointed solid timber. That is nothing more than solid timber, pieces of solid timber joined together with this glue finger joint. Okay? We join pieces of around 40 to 70 centimeters long, more or less, and we had a problem. We had a problem because we needed 25 meters long. Our wheel cell was 25 meters, but the machine that makes the finger joints has a length limitation of 9 meters. You will always have a problem with the limitation of length because of the machines that make the finger joints or because of the transportation, but there is always a problem when we design big structures. So it's quite common that we have to do assemblies on site for making the lath longer. Here we have, for example, 2 solutions for making these assemblies on site. This is the solution, for example, in the Mannheim multi-hole. It's a mechanical joint. Here the lath, the other lath, and you put 2 pieces of timber at the side and join with the fastener. So it's a mechanical connection. And here is a scarf glue joint that they use in the Welland Aula Limit Museum and also in the Savile Garden GridShells. What do you think we decide? We decide for this on the right because we thought it was nicer, aesthetically more invisible joint than the other. So we did this scarf glue joints for our PEMADE grid cell. This is some picture fabricating it. Quite a tricky job also because it is an inclined joint, so it's not easy to do. But again, problem with the glue. The glue, as I mentioned before, needs controlled environmental conditions, so we have to glue indoors. So we have to fabricate tables of 25 meters long. We used the laboratory, the corridor, the other corridor. The people were crazy because they wished that we finished this work quick. Yes, it was an adventure, but we did it. We continue that adventure with the glue lamp arches, the 2 glue lamp arches where the grid cell rests on. We needed 3 meters radio arch for our design, but there were no company in Spain that manufacture glue lamp arches of less than 4 meters radio. So this is, we always say, one of the main learnings in this project. How we did? In traditional way. We have to do it by hand. We create this formwork and then this very delicate work of gluing one lath, another, giving pressure. Yes, another adventure, but we did it and it was nice at the end. we should, when we design this kind of curved shapes, we first must be, or must know well, what is the limitation of manufacturing of the companies in your areas, but because this could be a problem in some cases. So this is a big learning, as I mentioned. Good, here is the manufacturing of the steel elements. At the top is steel support. This is a element, a movable joint that we design here at the top of the support. It has a curved shape, so the two glue lamp arches can fit very well on it. It can rotate, and also it can slide along this bar, so they adapt very well to possible manufacturing errors, and at the end it fits everything perfectly. This is the 6 layers of lath joined together by a bolt of 12 millimeters in diameter. Here in gray you can see the two families of laths in the longitudinal direction, the 2 layers. They are 75 times 30 square millimeters. And these in blue are the families of laths in the transversal direction. As I mentioned, we have there this 3 meters radio, so it's very small. So we solve it with the lamination of 3 thinner laths of 10 millimeters thickness this time. So we mechanical laminate with the screws, so we could bend it better. The shear blocking, in this case, was solved in each node, as you can see. So it was not necessary to include pieces of timber of shear to make the shear blocking here in between. So I think this solution, it was very simple, and it provides a lightness appearance also to the final view of the GridShells. Here are some details of the anchorage of the textile. It was solved with the round bar joined to steel plates that were joined at the same time to the timber laths. The textile make a big tension against the structure, like if it were a drum. So it was transmitted to the 2 layers of the GridShells through these pieces of timber here in between. We also designed this thin element here over the head of the bolts along the transversal layers to avoid damage on the textile when this is during the installation, as you see. And the lifting process was carried out by 2 cranes that lift the GridShells by the 2 arches, here and here, and put it on the steel support. After the lifting, the 2 movable joints were welded. These 2, they are welding here. And it was a terrible rainy day. It used to happen in Galicia. What can we do? The problems didn't finish. And here is a picture of the GridShells after the textile installation. And here another picture, almost finished, with this perimeter translucent wall closing the project. This is an appearance from inside. we finished the latch with the luxure in dark color to emphasize the contrast with the white. A detail of the nodal joint. This is the transversal layer. You can see here the three pieces that form this layer. In this picture you can see the curvature very well, I think. And this is one of my preferred pictures because it's an interview of, this was the moment of the first storage of timber. So I like it very much. Another detail of the support. The cantilever of 5 meters long. And another picture of the cantilever at night. I think the effect when the light is on is like a grid lamp, and is, I think, nice, the effect that we wanted to achieve. Good, so after seeing the design and construction process, I would like to share with you some of the previous research that we have to develop before designing this PEMADE grid shell, and it is related with the material, mainly with the material, and with the numerical model. I will start with the material, how we develop high-performance eucalyptus lats. But first I would like to come back again to this traditional elastic timber grid shell, Mannheim, Downland, Saville, and Polydome. All of them were solved also with the same product as we use in the PEMADE grid shell, this finger-jointed solid timber, with different species. The reason mostly was because they were species of high quality and available in the forest resources in the area. And all of them have moderate bending strength, usually around 30 megapascals. But in practice, for the radius of curvature that we used to use and the lag thickness, it's quite common that the initial bending stresses with this are very close, very, very close to this bending strength, giving no reserve strength to withstand another load, like for example wind or snow. Okay? And this is why in some cases, like for example in Downland or Saville, they had to bend the lath wet or with the material in green. Okay? And also the process of bending took several weeks, in some cases months, in order to help the dissipation of internal stresses. And I think this lack of strength in the products used to elastic timber in the elastic timber grid shell, I think it is one of the main barriers to the popularization of this type of structure, in my opinion. In our case, we use also a local timber, as I mentioned. We use Eucalyptus globulus. Eucalyptus globulus is a hardwood species. It grows in several countries around the world. But you see here, in Spain and Portugal, we cultivate around 50% of the forest worldwide. 50%. It's quite much. And if you take a look here, in Galicia, there is much density of where the PEMADE grid shell is built. Here, there is much density of Eucalyptus globulus. This is a picture of the tree. I know you know it. It's a very slender tree, so it is naturally prepared to withstand very high bending stresses. It is one of the 3 hardwood species in Europe with the best mechanical properties, together with beech and ash. It is classified as a D40 strength class, which means that it can be calculated with a characteristic bending strength of 40 megapascals. You have to realize that common species, like for example pine, used to be calculated with 24, 30, more or less. This is the range. And eucalyptus is 40. So, but even these high mechanical properties and also good natural durability that this species has, do you know what is the common use of this species? paper. It is used for making paper in the paper and pulp industry. It's a pity. So this is why from the university we are, since some years ago, working in giving an added value to the species by the development of high-performance timber products. For example, these high-performance latch for elastic timber GridShells. And the question is how to obtain high-performance latch. The process can be divided in 3 steps. We talked already about it, but I think it's worth to remember it very quick. We need first solid timber, but the solid timber must be structurally classified. In our case, in eucalyptus, we have maximum length of 3 meters because of sawing process of the material. Then, as I mentioned, we join solid timber with finger joints to get the finger jointed solid timber product. The maximum length depends on the finger joint machine, as I mentioned, depends on the factory. And then, if we need longer length, we have to make this kind of a glued scarf joint, in our case, on site. So we have these 3 important elements: solid timber, finger joint, and glue scarf joint. What is then the strength of the lath? We have to imagine the lath like a chain composed by 3 links. So the strength of the lath would be the strength of the weakest link, not? Yeah. In this case, the strength of the lath would be the minimum of the strength of the solid timber, strength of the finger joint, and the strength of the scarf joint. So how to obtain high-performance latch? Having all these 3 elements of high strength. We don't have any option. So now I will show you how we get high-performance solid timber, finger joint, and scarf joint for our PEMADE GridShell. Started with the solid timber. I said that eucalyptus is a D40, so keep in mind that we get 40 megapascal automatically by applying the visual grading criteria established in the Spanish standard. And it involves mainly to select boards with maximum size of notch of 1/3 the width of the lath and having maximum grain deviation of 10 degrees. And this is very easy to get. Both are very easy to get, so we could start with 40 megapascals very easy. But we have tested a lot of solid timber of eucalyptus in the lab, and you can see here some results, and we observe a certain correlation between modulus of elasticity that range in between 10,000 and 30,000 more or less in eucalyptus, and the strength. The highest modulus of elasticity, the highest the strength. So our idea was to make 3 groups of qualities according to the modulus of elasticity, from 10,000 to 15, from 15 to 20, and from 20 to 25. So if we use the groups of best quality, or the highest modulus of elasticity, we will automatically get very high strength that we could use, for example, in the most stressed area of our structure. We also tested a lot of finger joints using boards coming from these groups of qualities that I mentioned. We also tested different configuration of finger joints, of finger joint geometries. And I think, going very quick, I would like to show you this, some of the results that you get an overview, an idea, a general idea of the behavior. With the group 2, with modulus of elasticity between 15,000 to 20,000, we obtain 51 megapascals of characteristic bending strength for solid timber. And if we join together groups 2 and group 3, the strength increased to 56. For the finger joints, we got, for the same group, values a little bit smaller, but in both cases higher than the 40 megapascals that we get automatically with the visual grading criteria. So the strengths are high. They are characteristic values. And we also tested a lot of scarf joints with different adhesive, 2-component polyurethane and epoxy. And here I show some minimum values of strength. We decided for 2-component polyurethane, and we see that the strength is quite high, and quite high than the results get for the finger joint. So we didn't have to worry of the strength of the scarf joints at all. Okay, so in order to understand better the superior properties of the eucalyptus wood, I would like now to talk of one of the main of the key issues in the design of this kind of structure. I said before the elastic GridShells are bent on site to get the final shape, but we cannot bend as much as we want because we could break it. We have to control carefully the minimum radius of curvature, and we know how to calculate. The highest is, we can calculate with this expression, all come from the strength of material, the common strength of material expression. And as we can see, the higher the modulus of elasticity and the lug thickness, the higher the minimum radius of curvature, and the highest the strength of the material, the smallest the minimum radius of curvature that we can get. And this, this relation highlighted in red gives us an idea of the carving capacity of the product. These are specific material parameters both. And as an example, we see here represented the minimum instantaneous design radius of curvature for a lath with thickness of 30 millimeters. Just an example. For different species, and we have here eucalyptus of the same groups of qualities that I mentioned before. So we can see that with the best quality, we can get radius of almost 6 meters. If we compare it with another hardwood, like for example oak or chestnut, they are in 9.5. So this is very advantageous in our design. Not only that we can get a smaller radius of curvature, but also for the same radius of curvature, we could have an additional strength reserve, a margin of strength reserve for withstand the rest of load. Okay, and this is really important. And we could also bend in dry. We couldn't need to bend in wet or with the wood in green, like in the previous examples that I mentioned before. So all of this is quite advantageous for the design with using this species. Okay, so now I will show you some research, this case behind the numerical model that we developed. One of the key issues in the numerical models of this kind of the structures, as we mentioned during the corrections also, is to correctly adjust the stiffness of the joints, because the stiffness of the joints influence very much the out-of-plane bending stiffness of the structure, and consequently the stresses, the deformation, the buckling, everything. Okay? So what we did, we built a smaller prototype, a laboratory prototype, and we make some full-scale tests to this prototype before designing the bigger one, the PEMA de GridShells. We tested two configurations, this configuration with a single layer, the two longitudinal LUTs and one transversal LUT, and we also tested the configuration B that was double layer of the longitudinal LUTs and just one single layer of the transversal LUT. It has a 7 meters span and was resting also on the two shorter sides, this time on two LVL supports. Here you can see the loading test that we perform. We load it with water containers here at the middle, and we measure with photogrammetry. We measure different points at the intersection and also at the middle part of the LATs. As you can see, it was around, don't remember, 150 more or less target points in total. And we record the deformations of these points. This is the case of the single layer, the configuration A. Both configurations gave more or less the same results. Here is a picture from inside with the water containers hanging. And here are some details of the joints, of the three kinds of joints that we have in this prototype: the nodal joint, the joint of the grid shell to the support, and the mechanical connection of the transversal layer that again was solved with 3 layers of a smaller thickness, this time 8.3. All of them are mechanical connection, screws with different diameters as we see here. One of the important things that we should keep in mind is that mechanical connection have semi-rigid behavior. And semi-rigid behavior means that when several layers are joined with this mechanical connection, they appear some kind of sliding between them, as we see here. Okay? So there are always some slide that we have to consider in our numerical models. This is the representation of the deformation. When we have this multi-layer with a semi-rigid, it will have more deformation than a glue, than if the 3 layers in this case, or more layers, were glued, and less deflection than if we make it without connection. Okay? But this is important. An accurate modeling of the connection is key, as I say, to correctly predict the deformation. And we see here this phenomenon, again, with the thumb of the mechanical fastener. This is 2 layers of LATs, you see, subjected to a shear force, here and here. So we can see how the dowel is deformed and the wood is subjected to some kind of compression. No? This is compressed here. This is the sliding, the movement, the displacement, and we can calculate the stiffness of this fastener as a ratio between the applied load divided by this sliding, by the displacement. And we call it a slip modulus. We can determine this with the Eurocode expressions. It is directly proportional to the diameter of the screw and directly proportional also to the mean density of the timber. So we have it calculated like this. Okay, no problem. How could we model it? Some of the group did like this. Yeah? We can use a spring. We can place it at the shear plane, and we can add a longitudinal stiffness equal to this Kaiser value of here. Yeah? This is the same approach exemplified in the nodal joint of the prototype, of the configuration A. How we did? We developed a system of coupling aligned, as you can see here. One end was placed in the longitudinal axis of the lath, and the other end was placed at the shear plane. And this one, at the shear plane, had also 2 springs perpendicular to each other. They can simulate the movements perpendicular to this axis. It is placed where the screws are. And the rotation around the axis of the coupling was also free. We give the stiffness, or we assume the stiffness of both springs equal, and we could calculate it, or we use this Kasser value, as I mentioned before, for the stiffness of these springs. Here we can see the view of the global model in Rhino, with the points determined by the photogrammetry, and they were implemented in Drupal, in the software Drupal. Here we can see a picture of the numerical model in Drupal. We apply a lat deformation structural analysis, and here very quick we can see some results. Here is the global deformations. I don't know if it's functional. No. At the top we see the global deformations of the whole prototype, and down the deformation of the 3 arches, transversal arches. In general, as you can see, I don't know if you see it well from there, but the experimental that are represented here in gray and the numerical that are in blue results fit quite well of the 3 arches. You see all the experimental and numerical deformation, but instead we can do a couple of observations. There are higher deformation at the load application point here in the experimental test than in the numerical model. Even if the total deformation or total displacement, that I don't remember, it was around 14 millimeters, 13 dot something, were down under the limit value of serviceability limit state, heavy concentrated loads could exceed the joint service range, causing local effect not accounted for in the model, like for example non-linear slip phenomenon in the joints. So this is why we also develop numerical models considering a non-linear behavior of the stiffness at the joints that we got from experimental test of joints at the laboratory also. And another observation is that the greatest displacement happened at the bottom of the transversal arch, as you can see here, here, and here. This is the without deform and before the loading test and after the loading test. So this is the higher displacement of the structure here. So it was very clear that we needed to have some kind of modification in the design in order to increase stiffness in this area down. And we decided for using double transversal lats in our PEMADE grid shell instead of one. We double these transversal lats for increasing the stiffness in this area instead, for example, of deciding for another solution like, I don't know, large cross-section edge beams or steel beams. I don't know. We decided for this. It was the reason. Good, so now for finishing the presentation, I would like to show you some work in progress, but I will show you some ideas of the project because it's not finished yet. We continue working this elastic timber grid shell, but this time we follow a new concept. This time we combine advantages of active bending, of traditional elastic grid shell, but we combine with advantages of digital fabrication of modern timber construction. And for this, we get it, we make it first by developing a high-performing product, this time of a board format, a panel format. I will talk now more about it. That it could be easily matching with the common 3-axis CNC. We are also developing a carpentry joint for the multi-layer system, so we can get with this solution higher stiffness and avoiding this sliding at the shear planes, this problem that we have when we use mechanical joints with several layers, okay, of lats. We use orthogonal nodes And we get it by applying some strategy of principal curvature lines machine. So first, regarding the timber product that we are developing, this time is LVL, made of eucalyptus globulus. LVL is laminated veneer lumber, all of you know, yeah? LVL is made of different layers of maximum 6 millimeter thickness, so you can imagine the defects are minimizing very much, so we get a very high structural product of very high performance or very high strength. We can see the strength here. We have here the characteristic bending strength of different products, some of them of the market. Here in blue, LVL of eucalyptus. And if we see, the strength is more than 3 times higher than common glue laminated timber of softwood. You see, GL24 here. And is also 70% higher than solid timber of eucalyptus, that is here. And is almost in the same range as the, let's say, the best product that is nowadays in the market, that is LVL of beech, of European beech. Is commercialized as Baubuche. I don't know if you have heard about it, Baubuche. We are in the same league. And here on the right, I show you the same picture as we saw before, but including the eucalyptus LVL in S version, that is with all the layers in the same direction, and the Q version, that is with a couple of layers crosswise. And in this case, we could get radius, minimum instantaneous descent radius of curvature of less than 5 meters. So even better than with the solid eucalyptus. About the carpentry joints that we are designing, I would like to remember first some of the traditional solutions. Here at the top are different solutions for the elastic GridShells, like Mannheim, Saville, Polydome, or the Welland-Dowland GridShells. All of them are solved, as I mentioned, with mechanical connections. It's typically to use one single bolt. We see here this bolt. We see here the bolt as well. Here there is another bolt. And the problem is that the hole to introduce the bolt make a loss of strength in the lath because we lose material. So they have this problem in all of these solutions. And again, they are always sliding between the layers because they involve a lot of shear planes. And here down are some solution of pre-carved GridShells, like Solemar, Thernheim Bridge, or Schwarz headquarters. They are solved with glue laminated timber of higher cross sections. You can see the numbers here. They are really high. And the joints are usually solved by traditional half lap carpentry joints. Half lap. We see here a half lap, here as well, and here as well. Again, the same problem. We lose strength because we lose height in this cross section. Here we lose material, we have less depth, less thickness, so we lost this height and we lost strength. So what is our proposal, our concept? Is this one that you see here. Is quite simple. We have here some kind of thickener, I don't know how it called, is thickening, some thickening, you see, that create the same effect, more or less, than the half-light joints that we saw before, but we have not loss of strength because we don't reduce the section of the lath, you see? So it is, in addition, we don't lose material in the cross-section of the lath. We can get this profile by machining them from a board in flat base position very easily in a three-axis machine, CNC machine. So yeah, we can have a single layer joint or a multi-layer solution, and also we can create multi-layer models and following this carpentry joint. Here I show you we work in different versions with different solutions. I show you here the version 1 of all wood solution. We can see here very well this perpendicular, this orthogonal crosses between the layers, represented in yellow. Some things here, it is a model of the joint. You see here there is here the contact plane between the two layers is inclined to avoid the sliding that I mentioned before. You see? Here is inclined and here also. So we prevent the sliding between the layers. Then the layers are joined by these wood dowel connections that you see here. And here is a splice joint to make the lath longer. You see? Here with this shape. We are working in the design of this splice joint to guarantee that the strength of this joint is higher than the strength of the lath. And as I mentioned, we are working with meshes of principal curvature lines. And again, I would like to remember some of the other meshing used to that of traditional GridShells, elastic timber GridShells, Chebyshev grids, following this Frey-Otto concept, like in Mannheim multi-hole, or geodesic lines, geodesic grids, following the Natterer concept for elastic timber GridShell. There are also GridShells designed with curvature lines, like for example the Solema Therm building that I show here, but they are not elastic. They are pre-carved GridShells. Here you can see the elements. They have bending in both axes of inertia. And to our knowledge, there are no elastic timber GridShell until now with curvature line meshes. So we are very excited because we are working in a kind of a novel concept. And yeah, we are happy of working in this direction. I think it's really promising. Some geometrical properties of curvature lines, I guess you know it, really. Orthogonal nodes, like I mentioned before. The surface perpendicular to the curvature lines, this yellow, where the multi-layer system would be placed, are developable strip, so it's advantageous also. And we could cover the GridShell with flat quadrilateral elements, because as you know, these 4 nodes are in the same plane. Yes, we couldn't do this with another grid, for example, a Chebyshev grid. These 4 nodes, you know that they are not in the same plane, so we have to go to other solutions, like for example a carved element, or divide this into 2 triangles. Okay, but in our case, with principal curvature lines, we could cover, for example, with quadrilateral glasses, would be a solution. And also, they can be covered with developable strips, as we see here. So all of these are very advantageous properties when we are designing our envelope in our design, following this strategy. These are some pictures of some initial models that we fabricated following this new concept. This is another model. And this is a first bigger prototype that we built recently. It was exhibited at the Matadero Madrid. It was built using plywood this time. And the version of all wood solution of joint that I showed you before. And it is around 8 meters span. This is another view. Here we can see the developable cover that we used. Here are some details of the joint. And another picture of it. And honestly, we are very, very happy of this decision of combining the concept of elastic timber grid shell with pre-carved grid shells and principal curvature lines, because I think it's very interesting way and very advantageous for the design. So now we are working on a bigger prototype. We are working in this moment in the design, so this time we will fabricate using eucalyptus LVL, no plywood, like this one. And I don't know, I hope to finish it soon, and I can share with you in the next month. And yes, we will see. So, yeah, that's all. Thank you for your attention. I hope you find it interesting.